Well, welcome back, everybody. Up until this point, we've been talking about classification all semester long. Today, we're going to shift gears to the related topic of regression. Regression is kind of like classification, but instead of predicting a class, now we're trying to predict a numerical value, usually on a continuous scale. So again, we're contrasting classification with regression here. And classification, the goal is that when you are given a test point X, you will be asked to predict the class of that point. And that's often a binary decision. Sometimes it's a 3-way or a 10-way decision, but it's discrete. Regression is, you're once again given a test point X, but now you're asked to predict a numerical value, generally continuous scale. So we've actually already seen an example of regression, because when we looked at Gaussian discriminant analysis, LDA and QDA, we not only did classification, we not only took in a point X and predicted whether it's in class or class D, but we also derived formulas for what is the probability it's in class C, what is the probability it's in class D, and that is regression on probabilities. So essentially, we didn't realize we were doing regression, but that's what we were doing when we compute those posterior probabilities for the different classes. So what I want to start with today is kind of a general view of what regression is, because in a sense, regression is kind of like a menu where you can choose different options from the menu and plug in different interchangeable pieces to get an objective function, which then we're going to try to optimize. So to do regression, there's a few things you need to choose. First, you need to choose the form of the regression function. We're going to call that function h for hypothesis. And so h, again, is a function of both the point x and the weights w, and outputs some numerical value. Again, the reason we're calling it h is because that stands for hypothesis. And that is, the hypothesis is the function that we're trying to fit to the points. First, we have to decide what is going to be the form of that function. Is it going to be linear, quadratic, something else? So you can think of this as being like the decision function that we use in classification. Except instead of outputting a classification, we're just going to output the value of the decision function. Again, that could be a linear, just the set of all linear functions, the set of all quadratic functions, the set of all logistic functions. The other thing we need to choose is a cost function to optimize. The cost function can also be called an objective function, as optimization people often do. And usually, the cost function will be based on some loss function. So there will be two parts here. We'll pick a loss function for each training point or test point, and then we'll pick how do we agglomerate all those loss functions together. But the expected loss. And so, for example, we might wind up choosing our cost function, the empirical risk, which is the expected loss over the training data. So that's the general scheme. So now let me lay out some of the options. I want to lay out a menu for you of what loss functions you can choose, what cost functions you can choose, and what regression functions you can choose. Oops, wrong order. Regression functions first. Of course, the most famous form of regression is linear regression. And here our weights are some weight vector w plus a bias term alpha. And so the hypothesis will just be w dot x plus alpha, which looks a lot like the decision function we use in a lot of linear classifiers. But now we want the actual value of that function rather than just the classification. A second thing we can do is we can go to higher order polynomials rather than just linear. So you could do quadratic or cubic or whatever polynomials. And fortunately, this is easy for us to do. We just take a linear regression algorithm and we plug in polynomial features as I described in lecture 4, and ta-da, you've got a polynomial regression algorithm. It's really that simple. So if you can do linear, you can do polynomial pretty easily. And a third, more interesting example is, which we'll visit later today, is called logistic regression. And here we are using a logistic function and fitting that directly to the data. So, notice that these are almost the same. It's just that when you go from linear to logistic, now you are applying a logistic function at the end to this linear function. And let's just recall what the function s is. S of gamma is 1 over 1 plus e to the power of minus gamma. So this last choice is a pretty interesting choice because you will recall from the last 2 weeks of lectures that LDA produces logistic posterior probabilities as a natural result of fitting Gaussians to data and then applying Bayes' theorem. So you could ask, if logistic posterior probabilities are what naturally pop out of QDA and LDA, then why not just take a logistic function and fit it directly to the data? You can skip the step where you're fitting Gaussians to data and just directly fit the logistic function. And when you do that, that's logistic regression. To be clear, though, logistic regression is for interpolating probabilities. You can't use it for general numbers. It's specifically for numbers between 0 and 1. So those are the main regression functions we'll care about this semester. Though you could say that neural networks are regression functions all their own. Let's move on to loss functions. So in all of these loss functions, they're going to have 2 parameters, z and y. And z is the prediction of our regression model. Or in other words, it's h, our hypothesis, applied to x. And y is going to be the true label for any particular training point or test point. And the most commonly used loss function is just the squared error. You take the difference between your prediction and the correct label and square it. But that's not the only alternative that exists. Some circumstances, like if you have really bad outliers, you might prefer to use the absolute error instead of the squared error. So you just take prediction minus true label and take the absolute value of the difference between them. In some ways that makes more sense, but computationally it's a lot harder to do, which is why it's not as popular as the squared error. And here's a very special loss function that's going to look a little weird, and we'll try to explain it in subsequent lectures. Pardon me, I need a minus sign here. Minus y times the natural logarithm of z, and then minus, well, 1 minus y times the natural logarithm of 1 minus z. And so this thing is called the logistic loss. It is also sometimes called the cross entropy. And I want to be clear that for this to make any sense, y and z both need to be in a very restricted range. It only really makes sense if y is a number in the range from 0 to 1, and z is a number strictly between 0 and 1. But it might seem like a pretty harsh restriction to say that our prediction has to be between 0 and 1, but that's actually what naturally falls out of the logistic regression, is that this value here is always between 0 and 1, so no problem. And once you've chosen your loss functions, then you can assemble them together into a single cost function that you want to minimize. And there's quite a few choices here, but by far the most popular, of course, is take the average of all the losses. And so when you do that, that's called the mean loss, because it's the mean of all the losses, obviously, or the mean of all the losses on the training data. One thing when you're minimizing this, of course, you can cross out this 1 over n, because whether that 1 over n is there or not, the minimum is going to be the same. The minimizing parameters don't change if you cross that out. But it's usually called the mean loss rather than the total loss, so we're going to leave it in. But that's, again, not the only choice, even if it's the most popular choice. Another choice is you could take the maximum loss and try to minimize that. And it kind of makes sense if you think your data are very good. If you think your labels are very accurate, then why not try to minimize the biggest loss so that all your losses are small, rather than having this weird between different losses with the square, with the sum. But again, this is less popular not because it makes less sense than the mean loss, but because it's harder to optimize. A third option, which is very similar to the first, is to take a weighted sum of all the losses. Or you could do a weighted average, but I don't want to normalize that, so I'm just going to write it like this. Let me say that this here, that is the Greek letter omega. It's not a W, but it's called a weight, but it's a different kind of weight than the parameters that we're optimizing in our regression algorithm. So apologies, but the word weight is overused in this context. Weight has two different meanings. There are these omega weights, and what these omega weights do is they say some points are more important than others. So if I make omega I big, that means I really want to make sure the error or the loss on point xi is not too big. If I make omega I small, it means the weight that this point isn't so important to optimize. And so if you think some of your points have very accurate labels or are very important for other reasons, and others are not, you can use weights to play favorites. But remember, there's also an underlying weights. So these parameters of our algorithm are, those weights are W, and the weights at the bottom are omega I. Now, those three are the most common basic used cost functions, but one thing we can do in addition to that is take one of the existing or popular cost functions and then add what is called a penalty term or a regularization term. So if you do that, then we say that we have an L2 penalized cost function or an L2 regularized cost function. And it's also quite popular to use not the L2 norm, but the L1 norm. So if we use that in our penalty term, then we call this an L1 penalized or an L1 regularized method. And we'll be talking about those last 3 lectures from now, I think. All right, so that's our menu. It's like pick one from list A, pick one from list B, pick one from list C, and then you can put them together into an objective function. Yes? So you're asking, are you asking specifically in the context of omega, or? Okay, just why do you want to do this? The reason you want to do this is because you don't trust very large weights. You suspect that if the weights are very large, that it's not because that's a correct representation of your data, but it's because of numerical instability or something else that is throwing off your data. That's the short answer for why you want to add these regularization terms. I'll try to give you a much more complete answer 3 lectures from now, but does that kind of give you what you wanted? Okay, good. Any other questions before I put these together? Yeah. No, the L1 regularization term is not squared. Oh. Ah! My hands must be on automatic drive today. That's very sorry. Thank you for pointing that out, because that was really awful. I accidentally put a squared there. That should not be squared. The L1 penalty term is not squared. So my apologies for that mistake. Thanks again. Man, I definitely wouldn't want to leave that error uncaught. That is important. All right, so let's take these menu items and put some of them together. So I'll give you a list of 7 very well-known regression methods. Of course, the most famous is least squares linear regression, which I'm betting almost all of you have heard of before, if not studied in some other class. And there we take options 1 and a and little a. So linear regression function, error squared loss functions, and take the mean of all of the loss functions and optimize that. Of course, there's also a weighted version of that. Weighted least squares linear regression is basically the same thing, except that I just add those weight terms. So cost function little c, we have a weighted sum of terms and optimize that. If we take basic least squares linear regression and we add an L2 penalty term, then that's called ridge regression. There's another method called lasso, which is similar to ridge regression, except it uses the L1 penalty term. But it's basically least squares regression with an L1 penalty term. We call that lasso. I'll tell you what that means later in the semester. To come to a method that's really different from the others, logistic regression is kind of a beast unto itself, and we'll talk about that at the end of today's lecture. This is, well, you use the logistic regression function and the logistic loss function, but then we're just taking the mean of the losses as usual. There are a couple of methods that use the absolute error instead of the squared error or the logistic loss. One of them is called least absolute deviations. This is probably the most popular method among these oddballs that use the absolute error. And so there, we're just doing linear regression, but we are looking at the absolute error instead of the square, and taking the average loss. Or if we, instead of taking the average loss, we want to take the maximum loss, then that gives us something called the Chebyshev criterion. Most of these names kind of emerged for historical reasons. It's not like one person went through and thought about what all these regression methods should be called in some coherent fashion. Instead, it's like a hodgepodge of weird names. Part of what's interesting about making these choices is that depending on what you pick from the menu, you could have a very easy or a very difficult optimization problem. So some of these are a lot easier to solve than others, and the ones that are hard to solve often have special purpose algorithms designed just to solve that optimization problem. But to summarize what the optimization methods are for these algorithms, the first 3 are pretty easy because they always give you a quadratic cost function. And so you can just solve those by minimizing them with calculus. Well, when I say just minimize with calculus, that's going to give you a linear system you need to solve. So maybe the hardest part is solving a linear system of equations, but there's lots of great software available to do that, so that's easy. The 4th option, lasso, is essentially a quadratic program, which reminds us of support vector machines, but it's a completely different quadratic program when you come down to it. Also, I think one with an exponential number of constraints, so you can't really solve it with standard quadratic programming software. You need a special purpose algorithm for solving. The one on our list, logistic regression, has a convex but not quadratic cost function. When you have a convex function, as I've told you before, convex functions are generally a lot easier to minimize than general functions because typically there's only one minimum, or there's a group of minima that are all connected nicely together, so they're easy to find. And typically we minimize this with gradient descent or Newton's algorithm. The last two can be expressed as linear programs. So anytime you want to use the absolute error instead of the squared error or logistic error, you now have a non-smooth problem with inequality constraints, and you need some algorithm that can cope with those. And again, as I said with lasso, the number of constraints might actually be exponential, so you got to be careful. So again, we've got this menu of different choices you can make. To some degree, you can pick and choose different things and put them together into an objective function. But then the question of how expensive is it to optimize that objective function, how easy is it to find software that does it well, is going to depend a lot on the choices you make, which is what makes some algorithms more popular than others. Any questions about this so far? Yeah. W slash means with. Yeah, just in case anyone's not familiar with it, W slash is a very common abbreviation for with, and for what it's worth, W slash O means without. Yeah. Say one more time. Absolute error, like you're talking about number or polynomial. There isn't necessarily a name for that, but many of these methods you can just replace the linear part with polynomial and it just works. So maybe all of them. As a rough rule of thumb, polynomial interpolation is very easy because if you can do linear interpolation, then you just add polynomial features and pretty much any algorithm will suddenly become a polynomial algorithm. So that works on almost all regression and classification methods, which is why I don't really special names for that. So I'm going to spend the rest of this lecture talking about two of these specifically. I'm going to go over least squares linear regression, and I'm going to go over logistic regression. The first part, and maybe the second part, will probably be review for some of you. But let's do it. All right, least squares linear regression is one of the oldest algorithms we talk about in this class because it goes all the way back to the great mathematician Carl Friedrich Gauss, who invented this in 1801, long, long time ago. And so recall that this is kind of the simplest choices you can make from our menu. We have a linear regression function. We take a squared loss. Maybe it's not obvious why that's the simplest, but when you take the derivatives, it becomes obvious. And the cost function being simply the mean of all the losses. And when you write out that combination of those three menu items as an optimization problem formally, it looks like this. Find a weight vector W and a bias term alpha that minimizes I'm leaving out the 1 over n here because as I told you, we don't need it. the difference between, this is the prediction, xi dot w alpha, made by our regression coefficients, and this is the actual label. So it's just the sum of squares of errors over all of the training points. Let's find the w and the bias alpha that makes this as small as possible. And I'm going to put this in a box to remind you that this is a formally stated optimization problem, so then you can abstract that away and solve it. Let's see what this looks like visually so that we have a little bit more intuition for what this actually means geometrically. Figure from one of your textbooks. Introduction to Statistical Learning, figure 3.4. Example of linear regression. So we're given the red points as input, and we're asked to find this blue-green plane. And makes this blue-green plane special is, well, let's look at all of these little vertical bars that have been drawn from each point down to that plane, or up to that plane as the case may be. So we're looking at those vertical distances, vertical distance from the point to the plane. We want to minimize the sum of squares of the lengths of those vertical line segments. And that tells us which plane we should choose. So that's just what linear regression is intuitively. So let's get down to the math of how we do that. I want to talk about the convention that we've already been using throughout up to now and will continue to use for the rest of the semester. We assume that our input is an n by d matrix of sample points, which we call the design matrix. And n is the number of sample points, and d, of course, is the number of features in each sample point. We're also given a vector y of length n, which gives us the labels, but now the labels are not classes, now the labels are scalar values. And just to clarify what kinds of notations I like to use for this, well, let's actually spell out some parts of this matrix in detail. So you recall that our convention is that row I of the matrix corresponds to one of our sample points. Oh, wait. I want to change something here. Leave room for an extra column. So that row represents the ith sample point, but usually when we just write a sample point xi, we want it to be a column vector, so that's xi transpose, because it's the matrix. Also, sometimes we're interested in talking about the columns of this design matrix. And so if I have a feature column and I want column I, then I'll use the notation x, and then the subscript will be an asterisk, kind of a wild card, and then a j to represent that column. And of course, we also have a vector of labels. N of them, one for each sample point, and we call that vector y. And usually the number of sample points is greater than the dimension of each sample point. So that matrix is taller than it is wide. But not always. All right. One thing that all these regression algorithms and methods are going to share with the perceptron algorithm is that we have to think about whether or not our plane, our decision function, our regression function, is going to be 0 at the origin or not. Recall that the basic version of the perceptron algorithm essentially gives you a decision function that passes through the origin. And in general, that's too limiting. That's not what we want. What we want is an arbitrary plane that may or may not pass through the origin. That was true of the perceptron algorithm. That's true now. And we're going to fix it the same way we did with the perceptron algorithm. We're going to add a fictitious dimension. And so you will hopefully recall that trick, but if not, I'll remind you. I introduced this in lecture 3. And the idea is that what we want is a hypothesis that is linear with a bias term, alpha, so that it doesn't have to pass through the origin. It doesn't have to be 0, 0. And so we write this as follows. We x, our input, and we write it as x1 and x2 and so on. Let's suppose we're just working in a two-dimensional feature space for now. And then what we do is we throw a little 1 on at the end of the vector. So we're just taking all our input points, sample points, and increasing them by 1, adding a 1 at the end of every vector. And we're going to also lengthen our weight vector. So if before we had a two-dimensional weight vector with W1 and W2 in it, now we're going to have a three-dimensional weight vector where we add an alpha at the end. All right, so how this affects the design matrix is that I'm now going to make a design matrix, or at least imagine a design matrix, where I've added a column of 1s to the end of the matrix on the right-hand side. And I want to be clear that I'm not going to rename X when I add those extra columns, because I don't want to have overly complicated notation. So now, from this point on, X is going to be an n by d plus 1 design matrix. But I'm not going to change the name of X. I'm going to keep calling it X. W is going to be a d plus 1 vector with the bias term at the end, but I'm not going to rename it. I'm going to keep calling it W. So I hope that's clear. With that in mind, now we can go back and just do linear regression. The function I want to remember, I want to optimize this thing here. I want to minimize that. It's now possible to write that in a simpler matrix notation. So let me do that. But let me be clear that this is exactly the same optimization problem that I already wrote down. I'm just writing it down in a different notation. So this box means exactly the same thing as the last box. But gee, it sure is a lot more concise now. Okay. All right, so now our objective function is just matrix X W minus Y. Take the norm, square it. This has a common name in the literature on least squares optimization, or least squares regression. It's called RSS of W. And RSS stands for residual. All right, so we want to minimize this thing, so we do calculus. We take the gradient and set it to 0. W. Let's expand out the square. That makes it a little more clear. So when you write it like that, it's not too hard to see that the gradient of RSS with respect to W is 2 times x transpose xw minus 2 x transpose y. And that last term's a constant, so it just disappears. All right, so if we want to minimize RSS, then we set the gradient to 0. And that implies that x transpose xw, let me get a little extra space there, is equal to x transpose y. Now, what I want you to notice about this is, first of all, x transpose x is a square matrix. It's a d plus 1 by d plus 1 matrix. Second of all, W and x transpose y are both vectors of length d plus 1. And thirdly, we know the value of x, that's part of our input. We know the value of y, that's part of our input. We are trying to solve for W. And so, with that in mind, it should be clear this is a linear system of equations that we want to solve for W. This system of equations has a name. They're called the normal equations. All right, but this is our solution. So we've solved the problem. You need to have some software that can solve a linear system of equations, but that's very easy to find, especially since x transpose x is symmetric. So solving symmetric linear systems of equations, there's tons of software out there for doing that efficiently. It's one of those problems that have been studied to death. You can use, most likely you'll probably want a solver that uses Cholesky factorization or the conjugate gradient method, depending on circumstances. But this problem is now solved. Except, well, there's some things that can go wrong. The main thing that can go wrong is x transpose x might be singular. Now, when you have a linear system of equations with a square matrix, as you may know, when that square matrix is singular, either your problem is under-constrained or over-constrained. This problem is always under-constrained. It is never over-constrained. There is always at least one solution to this problem. Sometimes there's infinitely many solutions because it's under-constrained, but never are there 0 solutions. And there's going to be a discussion section where you find out why. So I'm going to leave that for discussion section, but it's something you should know. The geometric thing that's going on here is that if x transpose x is singular, it means that all of the points lie on some common hyperplane. They don't really use all d dimensions of your, or d plus 1 dimensions, pardon me. They don't really use all d plus 1 dimensions of your space. So that's what's going wrong. But you will notice that X transpose X is always positive semi-definite, maybe not positive definite. You hope it's positive definite because then it's easy to solve. But it's always at least positive semi-definite and symmetric. All right, leaving aside the possibility that this might be singular, we'll come back to that later in the semester and talk about using the pseudo-inverse to fix that. But for now, let's just consider the case where we can invert that matrix, X transpose X. Then we can use a linear solver to find the value of W. All right. It is nice to write out explicitly what W is for a minute, just so we can talk about it. That value is the inverse of X transpose X times X transpose times Y. Again, I want to emphasize, in general, you do not want to take a big matrix and compute its inverse. That's slower than solving the linear system directly by some other method like Cholesky factorization or the conjugate gradient method. Computing an inverse is unnecessarily slow. So the main reason we want to look at this formula is not because that's how we're going to compute it, but because we want to just see that W is a linear transformation applied to Y. So someone's giving you these labels, and you're doing a linear transformation, and that gives you the weights. So this linear transformation that we're applying to Y has a name. It's called the pseudo-inverse of X. And the notation for that is X with a superscript plus sign, or sometimes a superscript dagger, depending on who's writing. And the pseudo-inverse here is a d plus 1 by n matrix. Remember that X itself is an n by d plus 1 matrix, so we've just swapped the two numbers there. So again, we're never going to compute X plus directly, because we don't want to compute the inverse directly. But again, we are interested in the fact that W is a linear transformation applied to Y. And typically, X is not usually square. So X doesn't have an inverse. If a matrix is not square, it doesn't have an inverse. But nevertheless, every matrix has a pseudo-inverse, which we'll explore more later, late in the semester. But for now, what's interesting in this context is that if X transpose X is inverse, then X pseudo-inverse is a left inverse of X. What does that mean? It means that if I multiply the pseudo-inverse of X by X, well, let's fill in the value of the pseudo-inverse here. Well, what do you know? This here is the inverse of this. So when you multiply them together, you just get the identity matrix. And just to be clear, all these matrices here are d plus 1 by d plus 1 matrices. So that explains the name left inverse. If I put pseudo-inverse on the left of X and multiply them together, I always get the identity matrix. Another thing I think is really interesting to observe is that, well, first of all, let's think about what values are predicted for the labels. Once after we finish training our regression method, what predictions does it make? in general, those predictions are not the same as the labels that were used to train it. So the predicted value of yi is called yi with a hat on it. Remember, statisticians like to use hats to mean a predicted value. And the predicted value is x times w. I'm sorry, w times xi for a sample point xi. So the inner product of w and xi. That's the value we predict. It's not necessarily the same as the actual value. So let me just visually explain what I'm talking about here. If we come back to this diagram, well, the vertical position of that point is I. The value that's predicted is the value at the other end of this vertical bar that connects it to the plane. So yi is the original label. Y hat I is the value that would be predicted for that sample point by this linear regression. And so those two things are different. And so let's ask, what are the predicted values, these yi hats? Well, we can write this in vector form. So that's a yi hat. Let's make a vector y hat that has all of the yi hats in it. And that we can just write as the matrix x times the weight vectors w. But the weight vectors were computed from the original labels by multiplying by the pseudo-inverse. So what this shows is that there's a linear relationship between the labels that you're given and the predictions that are made at the end. And the linear transformation, xx pseudo-inverse, is sometimes just written h. And by the way, this is an n by n matrix. And h has a name, and statisticians call it the hat matrix. Why do they call it the hat matrix? Because it puts the hat on y. Yeah. Why does the weight vector switch sides when we go from here to here? Well, this thing here is just inner product of two vectors, so I could have written it xi dot w. The reason I wrote it the way I did is just because I think of xi as being the thing that this is a function of, and w is constant. But when I went to here, I swapped them mainly because I want to always be using column vectors and not row vectors. That's all. You're welcome. All right, so what's the main thought that I think is worth thinking about the hat matrix is, in an ideal world, we would like the hat matrix to be the identity function. We would like our regression to fit all the data perfectly. But of course, in reality, the data generally cannot, you can't fit the data perfectly with a plane. You can't. So that's what happens in almost all real-world linear regression methods, if you have enough data for the number of dimensions. And so it's worth noting that if the amount of data is greater than the number of dimensions plus 1, then the hat matrix is singular, so obviously it cannot be the identity matrix. So that's just a mathematical way of expressing the limitation that if you have too many data points, you cannot, in general, expect to fit them perfectly with a hyperplane. All right, let me briefly state a few advantages and disadvantages of least squares linear regression compared to some of the other methods. It's the most popular regression method in the world for a reason. It's really easy to compute. There are other reasons, too, that we'll visit in a few more lectures, but are harder to state. Also, it usually gives you a unique solution if your data will allow it. Sometimes it doesn't, but usually unique and usually a stable solution in practice. But that's not true when the problem is under constraint. There's some disadvantages too, and the biggest one is that it is very sensitive to outliers. So suppose that some of your labels are just wrong, completely wrong, then the more wrong the label is, the harder it's going to pull your hyperplane away from the correct position because the errors that we're optimizing are squared. So our method tries really hard to reduce the big errors at the expense of the smaller errors of other points. So if you have a label that's completely wrong out in outer space, it'll pull the hyperplane out into outer space. Extreme enough case. The other problem is that it sort of fails if X transpose X is singular, because you can't just solve the linear system. Again, that means the problem is under constraint and has multiple solutions, and we will talk later again about, in discussion section and later in this semester, about how the pseudo-inverse can solve that problem. So discussion section 6 is where this will be talked about more. Quick bit of history. Least squares linear regression was first posed and solved by, as I said, by Carl Friedrich Gauss in 1801. And the reason he did that, he was motivated by the fact that he wanted to predict the trajectory of a planetoid called Ceres. And so he wrote a paper using least squares linear regression to do that. And that paper is regarded as the birth of modern linear algebra. So any questions now on least squares linear regression? Is it always guaranteed to? Is there ever a case when you can't use the pseudo-inverse? No. The pseudo-inverse pretty much always works for least squares linear regression. And hopefully discussion section will make it clear why that's true. Question there? If the pseudo-inverse always works, how can we what? Oh, I'm sorry. I left out a key piece of information out, which is that when X transpose X is invertible, then yes, this thing is the pseudo-inverse. When X transpose X is not invertible, a pseudo-inverse still exists, and it's consistent with this definition, but it's not this definition. You have to do something. And when we will need to learn the singular value decomposition first, and then we'll learn what that something extra is. And that'll be late in the semester, though. So, but we will come back to that. Any other questions? Yeah. Which substitution do you mean? Are you talking about below that? This part here, just as I would suggest that you don't actually want to explicitly compute the pseudo-inverse, You don't explicitly want to compute the hat matrix either. Its main purpose is just understanding what the relationship is between the original y labels you provide and the predicted values, the y hats. So this is an entirely mathematical argument at this point and not something you would actually compute. Does that answer your question, or is there more to your question? How did I get from here to here? Oh. I wrote this here. W equals this thing times y. I defined this thing to be x pseudo-inverse, and now I'm just substituting it in for w here. All right, great. All right, so now that we've done least squares linear regression, let's move on and learn a little bit more about logistic regression, which is a very young algorithm by comparison. It was invented just as recently as 1958. By somebody named David Cox. And it's a very specialized sort of regression method because it's specialized to probabilities. It's used to interpolate probabilities. And so this is what you get when you mix together a logistic regression function with a logistic loss function. And then the cost function is the mean of all the logistic losses over all of the training points. And of course, the main limitation, or advantage, depending on your point of view, is that it can only interpolate numbers between 0 and 1 exactly. So the logistic regression function never goes outside this range. It can't even be exactly 0 or exactly 1. Now, one weird thing about logistic regression is that even though it's called regression, it's usually used for classification. And so essentially what I'm telling you is that although the input labels could be any number between 0 and 1, they can be any probability. In practice, the way the algorithm is almost always used is to have all the input labels be 0s or 1. So I've really gone back to teaching you classification now, but the way we're classifying is that we're trying to fit the posterior probabilities of a specific point being in a specific class directly to the data. Yeah? Uh-huh. Right. Okay. So coming back to linear regression, first of all, what applications would you use this for? Typical application would be you have a number of inputs to a chemical process, and you can vary the value of those different inputs, and then you want to find out whether what the outputs are, how big the outputs are, how they vary with the inputs. Or you want to check how the number of cases of some disease vary from locale to locale as a function of the socioeconomic class of the people in those locations. So those are typical examples of linear regression. And so your second question was about when do you use the predicted values? Mm-hmm. Uh-huh. Mm-hmm. Right. So here it seems like we're interested in the projected values. I would say that we are not super interested in the projected value for a sample point where we already know the label. What linear regression is going to be used for is I have some new test point where I have no idea what the correct label is. And so maybe there's this town and I know the socioeconomic average income or whatever of the people there, and I want to guess what is the probability of them, or the expected percentage of people who will get such and such a disease. And so I use interpolation to figure that out. So that's how you'll actually use these models. Everything I was talking about, the y-hats, was not about, it's not that you actually want to use the y-hats, because those are data points where you already know the answer, the correct label. Rather, we just want to think about what it means for the y-hats to be different from the y's and what that tells us about how accurate that regression is. Yeah. All right, so coming back to logistic regression, let me just quickly remind you that QDA and LDA are what we call generative models. We build a model of each class, and then we use that to compute posterior probabilities. Whereas logistic regression is the first example we're going to have of what's called a discriminative model, which means forget about building a model of each class. All we're going to do is build a model of the thing we actually want to predict, which in this case is the posterior probability of having a certain class. And so what we learned, though, from LDA and QDA is the fact that in classification, the posterior probabilities are often modeled well by a logistic function. So you might ask, why not just skip the step where we fit a Gaussian to these classes and go directly to trying to fit a logistic function to the data? And that's what logistic regression does. So let's now take a look at what the objective function looks like and how to optimize it. So we are still using the fictitious dimension. It's not just for linear regression, it's for pretty much all regression we'll want to use this. So remember, when I write down this objective function, that it's not that the bias term alpha is missing, even though you will not see it, but rather it's just hiding as the last component of the vector W. So now our logistic cost function is this. We're trying to find the weight vector W that minimizes, I'm going to call this cost function capital J. So it's the sum we could say mean, but I'm just going to say the sum of all the loss functions. You plug in that complicated logistic loss function that I showed you earlier. It's going to look like this. There's a big minus sign in front. So the loss function is yi times the logarithm of the prediction plus 1 minus yi times the logarithm of 1 minus the prediction. And so this is the thing we want to optimize formally. All right, so before we go on, I just want to show you what these loss functions actually look like in a couple of simple cases. Remember that the label and the prediction are just two scalars. So if we look at that loss function, it's actually pretty simple. And I'll give you two examples. So the one on the left, the horizontal axis is the prediction z. The vertical axis in this one is the loss function given that the correct label is 0. So, as you might expect, I mean, a loss function is supposed to go to 0 when z equals y, when the prediction equals the correct label. Here the correct label is 0, so when z is 0, as you can see, loss is 0, just like you would expect. And as you move further away, it gets worse and worse. And although you can't completely tell this from the graph, it actually goes to infinity at 1. So this loss function is absolutely adamant that if the correct label is 0, then you'd better not put a 1 there as your prediction. But the closer you get to 0, the less insistent it is. The graph on the right is just to show you what would happen if you actually had an input label that was not 0 or 1. As I said, this isn't used very commonly, but it can be. And so if I look at the loss function for prediction z and true label 0.7, then that's what it looks like, the loss function. So that loss function goes to infinity at both 0 and 1. So it's absolutely adamant that you cannot set it to 0 or 1. And as you would expect, the minimum is exactly when z is equal to 0.7. So our global cost function is made just by adding up a bunch of these simple functions. Now, what is very helpful to know is that these functions are convex. And in fact, it's not too hard to prove that the overall cost function, j, as a function of w, is convex. And I will actually prove that next lecture, but for now, just believe me, it's convex. And since it's convex, it's pretty easy to solve it by gradient descent. Gradient descent will, in general, find a global minimum. To do gradient descent, we need to compute some derivatives, so let's do those. First of all, we need to know the derivative of the logistic function, just the simple logistic function s of gamma with respect to gamma. So s prime gamma, that is, well, remember what s of gamma is. It's 1 over 1 plus e to the minus gamma. And if you compute that derivative, you'll find that it's e to the minus gamma over 1 plus e to the minus gamma squared. This can be simplified a little bit just by writing it out in terms of our original function s. So it's interesting to note that the derivative of s is s times 1 minus s. We'll use that to simplify our functions a little bit. But no, let's actually look at that function and its derivative so that we can get a feeling for it. I hope you remember what the logistic function looks like, but if you don't, here it is on the left. So, horizontal axis is gamma, vertical axis is the logistic function, s of gamma. And on the right-hand side, we have the derivative. So horizontal axis is also gamma. Vertical axis now is the derivative of the function on the left. Yes? D gamma instead of what? Oh, yeah. Whoops. That's right. Thank you. So hopefully the graph on the right doesn't surprise you. What it's showing is, well, first of all, it's always positive. The s prime is always positive, because you can see s is monotonically increasing. And second, you can see that the slope of s gamma is biggest right at 0. And indeed, s prime is biggest right there, and it's equal to 1/4. So I want to now compute the gradient of our cost function j. And for that purpose, it's a lot more pleasant to read if I use a little shorthand here. I'm going to use s subscript I as a shorthand for the logistic function applied to xi dot. So essentially, the predicted value at the point xi. With that shorthand, now I can write the gradient of our cost function with respect to w as minus the following sum. Well, let's just peek again at j itself. Essentially, we're interested in this part here. There's a logarithm. Remember that the derivative of a logarithm of something is 1 over something. And slightly more complicated rule applies here, but that logarithm is just going to 1 over something. So this is going to be yi over si. And then we have to apply the chain rule. So there's also a grad si. And then the second term of the loss function is going to come out to be 1 minus yi over 1 minus si times the gradient of si again. So we can simplify that as follows. We can move the grad si's out of there. And remember that the gradient of si is si times 1 minus si, and then by the chain rule, we also get out an xi there. And it turns out that all of this stuff here simplifies more than you would expect. It's pretty easy to jump from that to, hey, this is just yi minus si times xi. So hey, that got really simple. Also, I can further simplify it by putting it into matrix notation and getting rid of the summation. So you can actually write this as just minus the whole matrix X transpose times the vector Y of labels minus, I need to explain what this last bit means. That is, the idea is that we're going to compute X times W and then apply the logistic function S element-wise to every entry in X times W. And if we do that, that's going to give us a vector that contains S1, S2, and so on up to Sn. But this is applying S component-wise to XW vector to give you another vector. And so I have just completed deriving the gradient of our cost function j. And so now what we want to do is we want to apply the gradient descent rule to take a step downhill. So here is the gradient descent algorithm that you would use. That is a step of gradient descent. What we're doing is we're just taking W, we're subtracting the step size epsilon times the gradient. And if you, so this comes from there. We're just substituting in the gradient there. If you want to do stochastic gradient descent, you can do that too, but now you're going to want to go back to this version of the gradient, because we want to pick out just one sample point and do stochastic gradient descent on that sample point.